Hi, my name is Gabrielle Taylor. I'm going to be doing homework 1, part A, part 1. So I have a cylindrical tank with a uniform cross-sectional area of 1 meter square. It has a drainage hole at the bottom with a size of 0.2 meter square. The water has been flowing at 0.1 meters cubed per second for a long time, and the liquid level has reached a steady state. Suddenly, at time 0, the inlet flow is increased to 0.15 meters cubed per second. So what we're going to do is we're going to derive a differential equation describing the height of the liquid in the tank, and then we're going to simulate the response using Excel using Euler's method, and then we're going to do Python, and we're going to do scipy.integrate. Solve this. So the first thing that we want to do is we're going to do a differential equation, right? So the first thing is let's kind of draw out what's happening. So we have a tank, and we have a flow going in, right? And so we could say this is our Q in, right? There's a flow going in, and then you have a flow going out. So this is going to be our Q out, right? So we have flow going in, flow going out, and then this liquid inside is at some height, right? And then, of course, we have our cross-sectional areas of the tank. Here we have our cross-sectional area here. And then at this drainage hole, we have its cross-sectional area as well. So the first thing that we are trying to figure out is what is changing in this problem. Well, we're trying to figure out is the volume is changing, right? Volume of liquid is changing in the tank. So we could say dV dt, right, in respect to time. So one thing the volume is, it's going to be our cross-sectional area multiplied by the height. So it's V, the AC, height in respect to time, right? So what we know about this specific problem is that the height of the liquid is changing, but not the cross-sectional area. So we can actually pull out the cross-sectional area out of that derivative. So it's dH dt. So we have we have the cross-sectional area, and then we have dH dt, right? So why is this changing, and how is this changing? This is changing because of our Qn minus our Q out, right? The flow going in and the flow going out is what's making the height change. So we want to figure out right now what is our Q out, because we're given our Q in, we're given the flow rate, we're given the steady state flow, so we know that. But all we know is that our Q out is based off of our gravity of the tank itself, right? It's based off of just the water flowing out, right? And based off of the size of the hole. So what we could use is Bernoulli's equation. So Bernoulli's equation is P2 minus P1 over our density, and then it's going to be plus, and then our gravity, and V2 minus V1. I'm going to make that smaller so to fit everything. Okay, and then we're going to add this with our velocity at 2 squared minus V1 squared over 2, right? So this is Bernoulli's equation, and this equals 0. So the first thing that we want to look at is our pressure, right? So our pressure at the top of the tank, at the top of the liquid, and then the pressure at the bottom of the liquid. Not really necessarily the flows, but the top of the liquid and the bottom of the liquid, right? So right here, this is 1 atmosphere, right? Because it's just 1 atmosphere. It's not closed, like it's not a closed lid. It's open to the environment, right? So the same thing with the drainage hole. It's still open, so they will have the same pressure. So they still have 1 atmosphere. So this would actually turn that to 0. So pressure does not have to be included in this. So then we have our gravity, right? So for this specific problem, I'm going to say that gravity is positive in the down direction, right? So what that makes it is, right, so Z2 is going to be the bottom height at the drainage hole. and then Z1 is going to be the top height at the top of the liquid. So this is going to make our height negative, but it is going to give us Z2 minus Z1 is going to be a height. And that's going to be a negative height because gravity is positive from what we said. So right now we have minus GH, right? Okay. Then the next thing that we have is we have a velocity at 2, which the velocity at 2 is what we want. That is the flow of the liquid leaving the cross-sectional area at the drainage hole, right? That's what we want. And then, so V1 is going to be the velocity at the top of the liquid. Not going to be the Q, it's not going to be the flow rate going into it. It's going to be the velocity at the top of the liquid, right? So we can assume that's 0 because it's not moving. It has very minor movement. So that's going to be, assumption is 0. So now we just have V2 over 2 equals 0, right? So then we're going to just solve for V2 because that's the velocity. V2, and we move over GH, right? So it's going to be 2GH, and that's squared, right? So that's helpful. So now we're just going to plug this in, see what we get. So we have the cross-sectional area, dH dt. Those are Qn. Okay. Qn, right? And then we have our 2GH, right? Well, we have just the velocity, right? We need to find the flow rate. And so we need to multiply it by the volume or the cross-sectional area, right? So the volume of the liquid that's leaving as well, right? So that's going to be Q out multiplied by that, right? So then this is our equation, but we want to just solve for the differential height, right? We're just trying to solve for the height change. So we just need to divide by the cross-sectional area of the entire tank. So that's 1 over AC, and then Qn minus A out AGH, right? So this is the equation we're going to use. This is going to tell us the differential height, right? So the next thing that we need to do with this problem is that, so the problem gave us the problem statement. It gave us our Qn naught, right? It told us that the tank at this specific flow rate reached steady state. So the height was not changing, the volume was not changing, and then at time 0, the flow was increased, right? And so the height is going to change. But we need to figure out where our height started in the first place, right? So we need to find our Q naught, pretty much, because we have our, sorry, not our Q naught, our H naught, because we have our Qn naught. So we're going to use this equation down here, right? So we're going to do dH dt, right? And then it's got to be our Qn naught, right? Because this is what flow rate was going in at that period of time, right? What was the height at that flow rate? Then you're going to have is your A out. No. So then you have your A out. And then you have your 2GH. I'm going to have this 1/2, right? So, what do we know about this? We know that this is a steady state flow, right? That the height is not changing, the volume is not changing. So this will go to 0. So now we're just going to solve for the height, which is going to be our height naught. So we just move it over. So we have our height naught, Qn naught, and then we're going to be dividing by our A out and 2G, right? And then we move it over, so this is going to be just squared. So that's just squared. So this is our H naught. So we'll use our Q naught to figure out what our H naught is. That will be the height, and then we'll find the differential change. We'll use that to find how the height is changing due to respective times, right? So that is the end of the differentiating part.
Okay. Um, So after we derived this here, so this is going to give us our initial height, right? What we want to do after this is we're going to want to do Excel for Euler's method. So before we do that, I wanted to solve for our dH. Since we're using Euler's method, we have to separate dH and dt. So I'm just going to separate that for our function in Excel. So it's going to be dH. So we have dH dt, and we have 1 AC and Q in and A out over TGH, right? So what we want to do is we're just going to change that to the change in height and the change in time. So it's pretty much just going to be delta H equals 1 over AC. Actually, I can change that from 1 over AC to the change in time over AC, so delta T. And then Qn minus A out of 2GH. Okay, so we're going to use this for our Excel to find the change in height. Okay, so let's go to Excel. Up here. So right now we have our cross-sectional area, so AC, and this is going to be equal to 1 meter square, right? And so then we have the next one, we have our drainage hole, so A out, and that's going to be 0.2, and that's going to be meter square as well. And then the next thing we have is we have our Q in naught, which is the flow rate that was going in for a long period of time at steady state, so Q in naught. And then 0.1, and then this is meters cubed per second. And then we have our time the inlet flow increase, so we have our Q in, right? No, it's Q in, and so that's going to be 0.15 meters per second squared. Okay. So after this, so we have our cross-sectional area, we have our A out, we have our Q in naught, we have our Q in, and then what we want is gravity next. So 0.9 meters per second squared. And then we have that, and we want our T end. Well, we actually want our delta T. So we want a time step, right? So this is going to give us a time step of what it is. So we can change this, but we're going to do this. 0.2. It's just going to be our time step multiplied by our seconds to see how many time steps that is, pretty much. So next, after that, we want to do is, so we have our height. So we just need our H naught at the moment. So our H naught. Okay, before I do this, I'm going to make these all have a name. So formulas, create from selection, yeah. Okay, so all these have a name assigned to it. So I'm going to pull up on my iPad the equation we derived. Okay, so what it is equals, so we have Q in naught divided by, and then we have A out times the square root of 2G. 2 times G. 2 times G. And then that needs to have that. And then, oh, I think it's this. Okay, that's good. Yep. That's fine. Okay. So we have our height initial right now. And then we have our time step, we have our gravity, we have our Q in naught, our drainage hole, and we have our cross-sectional area. So we should be good to start. So we're going to first make like just a number list and then make our time scale. So what you can do is you do, I think it's home, fill. Okay, so I'm going to do 0 here, right? Then you go over here to fill, and then series, and then let's say it's 10,000? Yeah, 10,000. Oh, Control Z, sorry. Series, and then, oh, I did that wrong again. Series, and then I want it in columns, and I want this to be 10,000. Okay, so there we go. And then we have our T, which this is going to be our T for our time step. So pretty much what we have to do is we're going to multiply this here multiplied by our dt, right? So time step. So then go over here and then you do double click. There you go. So this is our time. And then the next thing is we want is height. So the first thing that we have is our height. So the first height should be our height at time 0, which is our h naught. So just plug that in here. Yeah, I think that should be fine. I don't think that would... Oh, wait, no. I don't want that like that. I want it to be h naught like that. This is huge. 1 times h naught. I'm going to make this a formula name as well, so that we can just use it instead, so h naught. So that's our h naught, so what we're starting at. So then we have a dh here, which is going to be our differential change in height. So this is what we're going to use for our equation that we derived in the beginning. So it's going to be, our differential height is going to be, I mean, I could do it like that, I don't care. So I can do our dH dt divided by our cross-sectional area out, cross-sectional area, out. And then we're going to multiply this by Qn minus A out, and then multiplied by the square root, as T. Thing is missing. There you go. Okay. Okay, so unclap. Okay, so the problem was that over here I had the parentheses with squaring in here. I needed to square out here with the parentheses, and then out here I just rewrote it the correct way, and then the parentheses were encapsulating here, which meant it would be multiplied down here and then subtracted by this, which is incorrect. So this is the correct of what you should do. So then we have our h naught and we have our dh dt, right? So this should equal our h2 right here, h naught, right? And then we have this here. Why is it? Why is this moving? This is not. Our height not plus height. Oh, that's why. Okay, and then the reason why this wasn't moving is because I have it as our height knot, which needs to be just the cell here so that it moves down. So when you go like this, and then this here. Okay, now we have it. So now we have our change in height. So these two, so just go like this, and so we're going to add a scatter plot. Okay. Let's change this. Let's add a 0 in there. Let's make it smaller. Okay, so here's what our graph looks like. So this is not really an accurate way of making a graph like this for the differential height because we're using Euler's method. That's going to give us a round-off error. So we're going to use Python instead. That accounts for round-off error. So we're going to do that next. So I'm going to exit out of this and do that. That's why. Okay, and then the reason why this wasn't moving is because I have it as our height knot, which needs to be just the cell here so that it moves down. So when you go like this, and then this here. Okay, now we have it. So now we have our change in height. So these two, so just go like this, and so we're going to add a scatter plot. Okay. Let's change this. Let's add a 0 in there. Let's make it smaller. Okay, so here's what our graph looks like. So this is not really an accurate way of making a graph like this for the differential height because we're using Euler's method. That's going to give us a round-off error. So we're going to use Python instead. That accounts for round-off error. So we're going to do that next. So I'm going to exit out of this and do that. Okay, so now that we have Colab, so the first thing that we're going to start by doing is we're going to use our scipy.integrate. We're going to use the solve IVP because this is an initial value problem. And so let's just start importing our stuff. So we're going to import numpy as MP, and then we're going to, from the library of scipy.integrate, we're going to import solve IVP, and then we also want to, from, I think it's subplots, big subplots, plotly dot subplots. We're going to import plotly subplots. We're going to make subplots. Some subplots. Okay. So then we're going to do a shift enter. So the first thing that we want to do is do our initial values. So we have our cross-sectional area, and that is equal to 1 meter squared. Okay, and then we have our cross-sectional. I'm actually going to change these to non-capital letters because I think it's easier. so A out equals 0.2, and then meters squared. And then we have our G, which that equals 9.8 meters cubed per second. Sorry, meters squared per second. And then we have our Qn, well, we'll do our Q and naught first, I think. Yeah, Q and naught, no, yeah, Q and naught is equal to 0.1 meters squared per second, meters cubed per second. Okay, so we have a Q and naught, we have that, we have gravity. Oh, we need our Tn. So the difference between Excel and Python, we need like a time end. So we can have it as 10. We can always change it later. So it's not really necessary. We could always change it. It's not a fixed. So we have all of these. Let's make our height out, our h naught. So we're going to use the equation that we derived again. So our equation that we derived, so it is Q and naught divided by A out, let's put this in, A out times numpy dot square root of 2 times G. Okay. So we have that, Q and Q. And then we just need one more. And this is square root. Okay. So that is our Q naught. Shift enter. Okay. So the next thing that we want to do after that, so since we have all our initial values, we're going to create the function of the differential height and time, right? So we're going to define it, and we're going to just say dh dt, and then this goes based off of our vectors, right? So our vectors of this is going to be our time and our height. So what we could do is we could do our Qn, right? So our Qn is going to be 50% greater than our Q naught, so we're just going to multiply that by 1.5. And then we're going to return our function that we already created. We're not going to do the one that has just the split height that we used for finding the differential height change. We're going to use the full one because it gives you a different answer. So I'm going to do our Qn minus our AC, our A out times NP, tap that, tap. Okay, so NP square root 2 times GH, and then divided by AC. Okay, that's what we had. So then shift enter. Okay, so after that, we're going to do is we're going to do our, you could say result. So we can say our result. Our result equals our MP line space. Okay, so what we're going to do next is we're going to do our solve IVP function, right? So our solve IVP function is, the first thing they want is the function that we have. And then they want us to do is a time scale. So our time scale is going to go from 0 to Tn, right? And then our next thing that we want to do is we want to have from what height we're starting at, so our height knot. And then our method equals radu. And then we want our dense output to be true. Okay. So we have that. So shift enter. Okay, so now we want to start making our plot. So the first thing that we want to do is we could do our t-plot. T-plot equals, so we want to do a line space, right? So I think we do the result dot solve. Nope, that's for our h-plot. We want to do np line space. Line space, line space. Okay, and then we need to do from our time, right? So we're going to go from 0 to Tn. And then how many increments do we want to do it for? So let's just do 201. You can really change this, doesn't matter. So then we have our h-plot, right? So our h-plot is h-plot. Okay. And then we want to use this is we want to solve our IVP function using our t-plot, right? So we go result times solve, and then we go t-plot, right? Okay, shift enter. Okay, let's start making our graphs. So first thing that we have is let's do fig equals make subplots. Right? Make underscore subplots. I think. Okay. So now we have our figure equals. Okay, so our figure is let's do fig. We do fig dot add scatter. So we're gonna make a scatter plot, and we're gonna have our x be our t, and then our t plot, and then our y being our h plot. M equals h plot. And then we want to have 0, right? Okay, and then we're just going to do fig update. Fig dot update equals, and then we're going to do the height. Oh, no, fig dot update. Height equals 800. Length equals 400. Okay. I think it's fig update, maybe subplot. Subplot. That's bad. Okay, shift enter. Let's see what we get. Okay, there we go. So this looks much nicer. Okay, so here's our plot. Looks very similar to our other plot that we made. This one has a curve on it. This one does account for round off errors, so this is a way more accurate usage of initial value problems other than using Excel with Euler's method. So this is a good one. And then we're going to do part two next.
And then in the parentheses, we have the height of 3, our set point, minus the height 3 of the tank itself. And then we're going to adjust the value of the controller gain, so Kc, to the value where the oscillations in the graph appear to be neither growing or dying out. This value of the controller gain is referred to as the ultimate gain. Kcu would counter that in our later discussion, so we don't really have to focus on that right now. But to set the height 3 set point is to be 20% greater than the initial steady state of the third tank associated with the initial steady state of the inlet flow of Qn naught is going to be equal to 0.1 meters cubed per second throughout the 3 tanks in series. Okay, so let's first derive equations to use. Okay, so we're working with this right now. So we have our 3 tanks like we did in question 1. We only had 1 tank, but these tanks, let me move them so they look a little better. Yeah, that's good. So the 3 tanks are in series in that they are the same. So they're going to have the same cross-sectional area. They're going to have the same area of their inlet hole, right? Of their outlet. So we have a Q in going into this tank, and then we have a leaving Q out is going right directly into the second tank, and then second tank has a drainage hole that's going into the third tank. That third tank is leaving out, right? So these all have a height to this. So we have a height 1 in the first tank, and we have a height 2 in the second tank. And then we have a height 3 in the third tank as well. And then this is our Q in. And so, like in the first question we had, we were deriving a differential equation for the change in height. So we're going to use the same thing here. So what we used was dH dt, which is the differential change in height, with the differential change in time, equals to 1 over the cross-sectional area of the tank, and we're going to be multiplied by the Q in. I'm actually going to move this. So I'm going to move this down, get the Q in, and then minus. And so when we use Bernoulli's equation to find the differential, not the differential change, but to find the flow going out of the tank, we use Bernoulli's equation. So that was A out times the square root of 2g, and then the height we're using for this one, let's say this is just the first tank, so the height is going to be height 1, and so I'm actually going to put a height 1 over on the equation itself, right? So this is the equation we had. So this is the equation for the first tank. And so the second tank, so the differential height change in 2 over dt, it equals 1 over AC, and then the flow going into the height to tank 2, right, is going to be the outlet flow of height of the tank in height 1, right? So that's going to be A out of 2GH2, right? And then we're going to subtract this by the flow leaving this tank. Sorry, this should be 1. 2 is the next one. This is the height of the first tank. And then it's going to be A out of 2GH2. So these subtracted? Good. So now we're going to do the third one. Okay, so it's 1 AC, and then we have what's flowing into the tank is the outlet flow of the second tank, just like we did the second tank. So it's A out, and then 2GH2, and then minus A out of 2GH3. Okay? And then the next equation, our last equation we're going to be using, is the one that was given to us in the problem statement. It's going to be the Q in is going to be equal to Q in naught plus Kc, which is our controller gain, and then it's going to be multiplied by our height set point of the tank in 3. That's P minus the height of tank 3, right? So we could actually call this, what we're going to call this is going to be error, the error, right? Or you could call it like that. That's going to be the error. Casey is our controller gain, and so now we're going to code this. So let's code this. We have our AC out, we have our Q in not, and let's pull up the homework. Actually, let's pull up that. It says that we want our Q in not to be 0.1 meters per second squared, meters cubed squared. We have that here. We're going to, keep most of this the same. Same thing on the height as well. That's good. So what we want to initialize right now is the height of the height set point. We'll just do height set point is going to equal. So we want it to be 25% of the initial 20% of the initial height. So we're going to multiply that by height naught. And we're going to put in our KC. So our KC right now, I'll put it as 1. We're going to change this to find where the oscillation is not gaining or losing. So this is good for now. So let's go here. Let's do Shift Enter, Shift Enter. Okay. So after that, we're going to add a code in between here. We're going to define a different function for this. So we're not going to use the same function as last time. We're going to use our function. So we're going to define, we're going to say right-hand side 3, right-hand side 3 tanks, right? And so this is made up of time vector and just we're going to put it as vector for now because it's going to be more than 2. So the first thing that we want is our height 1. We're going to unpack the vector, right? So it's going to be height 1, height 2, height 3 is going to equal our vector, right? So the next thing that we have is, so once we have our height 1, height 2, height 3, we're going to put in our equation that we got about Q. So Q in is equal to Q in naught times, so our Q in naught, plus our KC value, our KC times our height set point minus our height of the third tank, right? So that is for Q in. The next thing is that we want to do, we're going to return each value of that height differential. So what we want to do is, let's kind of split it up and say we have our Q1 out, Q2 out, and Q3 out. So when we do our equation, it could be easier for us. So it's going to be an out, and then times the NP dot square root of 2, and then times G times, and then since this is Q out 1, we're going to have height. We're going to have height 1. Yeah. And then the next one is A out times the NP dot square root of 2 times G times H2. And then we're going to do out again. Okay, so this is going to be our equation for all of the leavings of each tank, the leaving flows at each tank. So what we need to do next is we're going to just return the function, right? So the function is going to be brackets, it's going to be Q in minus, or I'm going to put this in parentheses, Q1 out divided by AC, and then AC. And then we have our second one, which is our Q1 out divided by, well, actually, this is all divided by AC. So, okay, so this is divided by AC here. Okay, so everything is divided by AC. Minus our Q2 out divided by our AC again. And then lastly, our last one we're going to be doing is the Q3 out, sorry, Q2 out. Q2 out minus the Q3 out divided by AC. Okay, so just to check again, so the first one we have going into the tank is Q in, and the second one is Q1 out, and then Q1 out goes into tank 2, which has a Q2 out, and then for tank 3, Q2 out is flowing into tank 3, and then you have a Q3 out. All of them are divided by the cross-sectional area of each tank. Okay, that looks good to me. Okay, so let's change some of this stuff right now. So first thing down here is we're changing that function of the result to the right-hand side, 3 tank. The time is fine. We can always change that later, but I think it's fine for now. And we're having this as a height set point. So in each tank, the height set point is going to be the same as like a steady state flow. All of these are fine. And then we're going to change this here. So this is height 1 plot, then height 2 plot, then height 3 plot. Okay, and then we use the T-plot as that line space, that makes sense. And then we're just going to kind of copy this. Okay, and the T-plot is the same. And I'm actually going to cut off this 0. Shouldn't matter. Okay, so 1, 2, and then 3. Okay, that looks good. So let's do some shift enters on this one. So shift enter, shift enter, shift enter, shift enter. Let's see what happens. Okay, so we have our 3 tanks here. So we have tank 1, tank 2, tank 3, right? So we're not getting that oscillating at all. So it's kind of just steadying out. So let's change this to like 15, maybe. Let's see what this does. Shift enter, shift enter, shift enter, shift enter. Oh, shift enter, shift enter, shift enter. Okay. Okay, so we're starting to oscillate here, but it's kind of stabilizing at the end. So it's kind of losing. So we don't want that. We want it to kind of come more. So let's maybe make it like 35 or something. Let's see what that does. Okay. So 35. Shift enter, shift enter, shift enter, shift enter. Oh. Oh. the square root is invalid. So that means this is too high. So let's bring this down to 25. Let's see what that does. Okay, that's fine again. Let's see what this does. So too big. Okay, so we got a little closer at 25. So it's in between 25 and 35 that we know of. So it's gaining and then it's like dying out a little bit at the end. So we could do, let's do 30. Shift enter, shift enter, shift enter, shift. Okay. It's gaining a little bit though on this one. But just a little bit, not too much. So let's do 29. See what that does. Okay. Shift enter, shift enter. Okay. Okay. You can see that this oscillating is oscillating on both sides. It's not changing. It's not gaining or losing on all three tanks. So here it is. So that's the end of homework 1, part A.